Okay, everything is recording now. So let me share my screen. Can you see my notability?
Yeah.
Okay, good. Yeah. Okay. So if you guys remember from the couple of lectures that what we were talking about, is this people were in the waiting? 1 second. Was in the waiting? We have a couple of people we're talking about. We have a couple of ideas we talked about, right? We build everything using combinational circuit, right? And we looked into the gate level, right? And we looked into the data flow, right? And the data flow was what? It was using the assign, if you guys remember. Correct? Then we also looked into about how to implement circuits using the gate levels, but this is for combinational circuit. That means there is no clock associated with this work. Is this correct? Now, what type of circuit we built? We built full adder. You guys later on, we learned the fourth generate in the level of the RTL. And then, in the level of the test bench, we learn for loop. Right? Now, what other devices we can build using this combination of the gate level and assign from your point of view? Give me an example. Something else than full adder. Can you hear me? Hello? Huh? Hello?
Yeah, we hear.
Okay, good. So, I'm asking, what else we can build than, full adder?
A ripple carry adder.
Ripple carry adder. It is ripple carry adder. What else? What else is combinational circuit? Huh?
2-bit multiplier.
Multiply. Okay, what else?
A CLA.
Okay, CLA. Okay, but what else?
The N bit,
What?
the N bit for adder.
And bit for adder. What else we can build?
Multiplexers.
Multiplexer, yes. What else?
Encoders and decoders.
Decoder and encoder. Okay, what else?
Majority encoder.
What?
Majority encoder.
Majority encoder. Okay, what else?
Flip-flops.
Nah, it will not work like that. Somebody will tell me why it will not. It's not as straightforward to build a flip-flop using combinational circuit. Why? Do you have a reason why? Huh?
No clocks.
Yeah, there is no clock, but you can make a clock. It's not really hard, but there is a reason.
There's no registers.
The reason that end of the day, that with the gates we have, we can just build latch, right? And the tool we are using defining what is flip-flop. So if we build a custom circuit, it might work. But if we use the context of Vivado, it might consider this purely latch and just completely remove it. Does it make sense? Yeah, you give me a second, please. Yes. Okay, I'm in the lecture now in Zoom. No, I'll do my best. I'll do my best and I'll call you, okay? Bye. Okay, anyway, so do you guys remember what type of latch we have in digital circuit? What is the name of the latch we had before? From 2300.
Was it a D latch?
D latch?
JK latch.
What is D latch? Yeah, exactly. There is no D latch. There is no JK latch. There is not like that. There is just one latch in the wall. It's called SR. There is just one latch. You know why? Because guess what is this called? What does this stand for? Set. And this one is what? Reset. So you know how you can build latch or not? So you already have here NAND gate, and here is set. And then here is another NAND gate, and here is the reset. Then you go ahead like this, and then you go ahead like that, and then gonna be the Q, and this is gonna be the Q complement. This is what? This is called SR NAND based latch. There is another latch which is what? NOR. So or like this, S, and then there's another one like that, R, and then you go like this, you go like that, and here's the Q, and here's the Q complement, and this what? SR NOR based latch. Later on, they came and say the latch is not using the time, right? So they decided to add what? The clock. What is a clock? It's a train of pulses. But it has some special properties, this train of pulses. What is that special property? The beginning and the end is called what? T, period, of the clock, right? This clock, to be qualified to be clock, the off time has to be exactly the same as the on time. And also this equal T is gonna be periodic. So it's a periodic train of pulses. Then this is a clock. Then they come and say, okay, how are we gonna use this clock? They said, you have to understand what is in the clock. What is in the clock? There is what? There is levels. And then in the top of the level, there is what? Edges. So how many level and how many edge we have? We have 2 levels. What is the 2 levels we have? We have low and we have high level. Low, that means 0, high is 1. Then we have 2 events. What is this 2 events? This one is going from the low to the high. That means I'm what? Charging. So that's basically what they call it. What? It's called rising edge. Some other books they call it what? Positive edge. So far so good. Now the other one is going from the top. That means there is a charge and trying to decrease the charge. That means what? Decharging, discharging. So that means what? They call it falling edge. Other books, they call it what? Negative edge of the clock. What is this? Your flip-flop is using? Flip-flop is actually looking into this or that. So far, so good. Hello.
Yes, sir.
Any question regarding whatever I mentioned so far?
No.
You sure? Okay. Anyway, so historically, they built the SR flip-flop out of the latch, right? Then they found out that the state table is missing, and the truth table is missing one state. There is a state is not usable, right? Then they tried to build what? JK flip-flop to solve the problem SSR, but actually create a new problem, which is basically is called triggering. That means that state, it continuously will flip the data back and forth, 1 and 0, 1 and 0, 1 0, 1 0, 1 0, 1 0. Then they fix it, and then after they fix it, they break the JK flip-flop into two flip-flops. One they call it T flip-flop, and another one is called what? D flip-flop. The T is coming from transitioning. You know what I mean? So basically, this is really good for building counters. And the D is very good for storing data, which later on can be used to build memories. I'm not gonna go into reminding you again about what is excitation table and characteristic table, stuff like this 2300. I shouldn't be going through it. Any questions so far regarding what I mentioned? Any question? Hello. No question, right? Okay. Now, to access the sequential, it's called sequential, by the way. The flip-flop, that means sequential element. So to access the sequential part of the circuit in Verilog, right? You have to understand something is called always block. So there's a new syntax we're gonna learn today. It's called always block. So what is this always block? 1 second. Okay. So the always block, there is two ways for you to write always block. Okay. Always block for the RTL and always block for the test bench, right? The one for the RTL is the following. I'm gonna just make the example and then I will open the file and we can look into it. Imagine that the hierarchy of it has to be like this. Always at, you make like a list of they call it sensitivity list. Sensitivity list. Then here you say begin, and then you have here end. If you want to name it, you can just put a name here. This is the skeleton of using the always block. And actually, always block is the beginning of understanding how to write what? Behavior modeling. Forbidden some stuff for you. Don't ever add a sign inside always block. Don't ever access wire inside always block. What does it mean? So if I would like to make a process inside the always block, it has to be a register. It has to be what? REG, not wire. You remember the wire? It was what? Was a sign. You remember that? It was somewhere here. Here. Right? Don't ever go inside the always block and tell me I'm reading wire and you know there's an error. Of course it will be there is an error, you know, because always block is the process of making you storing something, and storing something that means it has to act like a what? A register. That makes sense? So here is the skeleton. How are we gonna use it? It's really quite straightforward. So if you involve okay, clock into the always block, then we have behavioral sequential circuit. Okay, if we don't use clock with always block, that will be what? Using behavior modeling for combinational circuit. What does it mean? It means the following. If I want to make for instance, a flip-flop in Verilog.
Can you go up real quick, Professor?
What? Tell me.
I have time to write that thingy.
I mean,
Thank you.
Copy of the writing, I will give it to you. It's recorded as well. Anyway, so let me make example. Okay, so now we already have here like a box like this, right? This is actually what? A clock, and here is input, and here is output. This is the flip-flop, right? Let's call this D flip-flop. Okay, I want to make it using what? Verilog. How I'm gonna make it? So maybe I can just say module space. The name of the circuit is gonna be D_FF, right? Then you know I open my parentheses, close my parentheses, and say input space clock, comma input space I, comma output space P, right? Somebody will tell me, is this correct or not? In terms of syntax, does it really looks correct?
Yes.
No, it's not correct.
Uh-oh.
You forgot the end module. And another thing, we said we're gonna use always block, right? We said everything it has to be what? Register for the output, right? So that guy it has to be what? Rig. Okay, so we can clean this and just make it like this, space rig space P. Now, how are we gonna write the skeleton? It's gonna be the always, right? So always at, and then you know what is inside the sensitivity list, then begin and end. And here I will just say FF, flip-flop, right? So what is inside the sensitivity list? The clock. This is called sensitivity list. What does it mean, sensitivity list? It means that, you know, periodically, if any change happen in this list, the body of the always block will be updated. Again, this sensitivity list, every single time periodically it changes, that guy will be changed. whatever inside this, whatever is written. You know what I mean? How can we make example like that? Now I have a clock, right? I can put the clock here. But how I'm gonna put the clock? I'm gonna write it like this, clock? Of course not. Why? Because I've just write it like clock like this. That means, you know, I mean the two levels and the two events. Do you agree? Because the clock, it has two levels and two events, right? I have to be very specific in what I'm gonna use. So in that case, I can clear the part. I can just write what pause edge space clock. Can you see what I did? Hello. Everybody okay? Or
Yeah.
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 So you pause it. What does it mean what I did? I'm saying every single positive edge of the clock, check this guy. And since this is periodic, says automatically forever will be checked. Right? Here the clock, right? Right? So here will be checked, 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 and so on. You don't need to talk, Eric, just message. Okay, anyway, so are we done? No, we need to write the relation, right? So when the positive edge of the clock happened, what happened was this? It's a D flip-flop, right? So basically I would say is D, no, it's D, I'm sorry, B equal I. We done. But the question here, there is this that's it or not for flip-flop? This flip-flop is not gonna work. Somebody can tell me why. Why this flip-flop would never work? Enable. What else? Do about the enable. Something else. B is which it is which is. What else? Think about it. Block assignment. Still, we're gonna talk about this. It's not. There's something more important. Come on, that's from 2300. Surprise me. Data can be something else. You want me to tell you? Okay. This is a sequential circuit, right? Anything sequential, that means, you know, the previous has a relation with the present. And the, you know, and there is a delay between of them. That makes sense? So any circuit in the world, sequential, it has to have what? Initial state. Who is making the initial state for us? Reset. This circuit is missing what? Reset. Do you remember that or not?
Yes.
So what does reset is doing? What is the job of the reset?
It sets the initial state to 0.
Exactly. So in that case, we need to clean this part and go on here, clean this, and this comma, reset, right? Then we go inside this skeleton and say, you know, if, now I'm using if statement, right? If reset, and I write it like this, that's it. So what does it mean here? When I write if and between the parentheses, I just write reset, it means that, you know, if the reset is high, But if I want to write, if the reset is low, I can write it like this: reset equal 0. Do you remember the slides I gave it to you? You will find it there. Okay, so look, it's gonna be reset equal 0 if you want to monitor what something will happen when the reset is equal 0. But for us, let's make it reset is equal 1. So, you just make it like that, okay? Then, normally, if you are just testing one line under the if statement, you don't need begin and end. But if you're gonna make multiples, you need begin and end. So for instance here, if resets high, P equal 0, right? Then, else P equal I. That makes sense? Why I didn't make begin and end? Because end of the day, this is just one line. But if you have a multiple line under this if statement, you have to make what? Begin end. So it should be like this: if reset begin b equal 0 end. Then you go else begin b equal I end. This can happen if you have b equals 0, something else, something else, something else. But here, because there's a single line, I just use it like that. Does it make sense? Okay. Last part before we will hopefully, Vivado open so we can start looking into my Vivado. Vivado is taking forever, so I apologize about that. So Vivado. There is something also you need to know about it. It's called blocking versus non-blocking. Blocking versus non-blocking. From your, if you heard about it, what is this? I'm just curious if you guys heard about it or not. What's blocking? So blocking, use equal. Non-blocking, you use less than equal. Can you hear me? Again, blocking, use equal. Non-blocking, you use less than equal. In the sequentialism, we have to use non-blocking. Combinational, use blocking. You will find it in the slides, by the way. Let me find it. I think that's, let me see if you have it or not. I think I give it to you. Can you guys check the slides? I give it to you. Let me just open one here and then can share it with you. Okay. So we are looking into what the courses. Yes, you found it, right? I'm just trying to open it so you guys can see it. Later on, we'll fix the Vivado anyway. Last page, exactly. You're right. Everybody can have access to the slides, right? Okay. So open it and then we can read it together. So 1 second, let me just get here the slides here. gosh, this computer is ridiculous. Anyway. Okay, so here, combinational circuit. Here, sequential circuit, which is involving clock. The definition by the document I give it to you, it means that I execute in order. So I execute pieces, I go to the other pieces, I go to the other pieces. It's block. You know what I mean? And the whole entire idea about it, since you really don't have any problem with timing, better for you to use the blocking. But since we are working with the clock, the clock it's really quite tiny. So here, right? Don't think this is really huge, right? This is really quite itty bitty tiny, right? And if you are running in a high frequency, end of the day that can be actually 1 nanosecond, or maybe half nanosecond or something. So if you do a lot of process under this, you will have something is called what? Violation in timing. That's why you prefer to be non-blocked. That means you execute everything in what? Parallel, and leave everything by itself, finish by yourself, done with yourself, until I can solve the problem, and the tools will take care of that using what's called mathematical forms. So for our example here, right, we are building what? D flip-flop. So should we use blocking or non-blocking?
Non-blocking.
Exactly. So is whatever I wrote here is correct or need to be fixed?
Needs to be fixed.
Yeah, so in that case it has to be like this. Easy peasy, right? Okay. So to summarize what we learned today, we learned that there is something is called sequential circuit, involve clock, and this clock has levels and edges. Then we learned that we have a bunch of flip-flops coming from SR latch, right? And from there, we learned that, to start talking about, sequential circuit, we can actually use what? Behavior modeling. And the behavior modeling we are using, it can also be used for building combinational circuit. But then, we met some limitation. And limitation what? You have to use registers. You cannot have a sign inside the always block. And then, we define the blocking and non-blocking. And we said, the non-blocking will be the best case for building sequential circuit, while, the blocking will be great for the combinational circuit. Correct? And we already talked about inside of reset and, how the reset work and, what is important in the sequential circuit. Now, let me try to turn on my, what's called, my Vivado. Hopefully it will work. I don't know what's going on with the laptop at the moment, but it will work eventually. It just need to be clicked 17,000 times. 3, 4, 5, 6, 7, 8, 9, 10. Okay, I just clicked as many. So once it will open, we will just try now to write a code in front of you for a D flip-flop. And then, you guys can with one D flip-flop, you can actually work on making it what? Register, right? Using the full generate. That makes sense? My gosh, this Vivado is really killing me. Let's see. Are you guys on campus or what?
Yeah, I'm on campus right now.
I don't know. Did you get the message I sent you yesterday? Yes. Good. Yeah, I mean, this COVID thing is no joke, so watch out. I think I have one Vivado open, so I believe while I'm working with you, many Vivados will be opening. So I have to wait a little bit to close the rest. Okay. So, oh my gosh. It's amazing. I love this computer. Okay, anyway, now I'm gonna close this. And then I share screen. Share screen with you on my laptop. Okay, let's share my screen. Share screen. Let's close that first. Okay, everybody can see my Vivado, right?
Yes.
Okay, good. So now, if you start looking into the project, right? Let's create a new project, right? So create a new project. Oh, you know what? Leave it. It will take time. 1 second. Oh. Oh my gosh, she's opening a new one. Wait a little bit. Wait, Mason is here. Mason, I like Mason. Oh, I have more. Wait. Cool. Cancel. Okay, cancel. Have you seen a laptop like that? It's a piece of, it's an icon, Oh my lord. 1 second.
Professor?
Yes. Yes. Hello. What's up?
Are you gonna do the online for the lab too?
I don't know. It depends on how I feel. You know, let's see my situation. And also trying to take a PCR test to see whether that I have a COVID or not, you know. I'm taking tests to check if I have a COVID or not. If I'm negative, I will come. If just a flu, it's a flu, you know. But you know, if it's COVID, you know, I don't want you got sick, right? The idea for you to learn is not to get sick in this place. Anyway, can you guys see my my screen or not? Can you see Vivado or not?
Yeah.
Okay, now I'm saying at source, create new design, and I would say create file, and here I would say what d underscore ff like this, right? Then I will just go and say finished. Then I will just go ahead and click. No, it's not this one. We need what? We need a clock. We need a reset. We need input. Let's call it I. We need the output, right? Input. This is output. And then, you know, that's it, right? I'm going to show you multiple ways. It's crazy a little bit, but this is fun. So now we created, of course, you know, it's say updating there. And then, you know, the D flip-flop is there, right? Now we're going to look into our code. Our code, you know, I like to be more organized in this code. So I will just like push something like that. Okay, now this is going to be rigged. Because, you know, the default is wire, okay? Now, always at positive edge of the clock, begin, end, and then there you can say if reset, then, you know, p equal 0, else p equal I. That's it. See, we wrote the whole entire thing. Now, the number representation in the slides you have seen, right? So for instance, the P and I are single bit or multiple bits?
Single.
Exactly. So maybe I can make it like this, comma B0. Did you see what this mean? It mean binary. The one before the B, it means that, you know, it's a single bit. And then, you know, the value of it is 0. Cool, right? Or I can write it different. I can just make it like comma D0. Make it decimal, but still 1 bit. You know what I mean? Or make it octal. So 0. Make it hex 0. Do you see what I'm doing or not? So the compiler, if you write 0, it's okay. But, you know, normally in the tradition, you have to know that how can you represent numbers in the Verilog. That makes sense? So representing number in a Verilog in a single bit is like this. That's it. Okay. Any questions so far? Any question? The question, okay. Anyway, now we are being built in front of you a single bit flip-flop, right? How are we gonna test that? So, you're gonna go here and create simulation and create D flip-flop. TB maybe, yeah, that's it. And then, just say no, thank you, I don't want anything. This bench doesn't have any specific thing. And from whatever we learned from the previous example, we take a copy of those. And then, we'll just go in a simulation. And we have many simulation. We have this one we need. So we click on this, right, and say sit as a top. So then, we are running this specific test bench. And then we go inside that one. And then, we can just push this a little bit. And then I can go here and just boom, copy like this. And then I just go like that. If you guys remember what I'm doing, dot. Hey, I understand. Dot. Then we remove the module. And from there, we write a name for that. So let's call it, FF generate 1. That means this is the first attempt of us. Then we go here and make our what? Blocky thing. Right? Now, we said to make a test bench, the input will be registered. Do you guys remember that? And the output will be wires, right? So here we're gonna be what? Reg clock, reg reset TB. There is gonna be clock TB. Then reg ITB. Then wire PTB. Correct? We're gonna put here the clock. Reset TB. I. And we need what? P. Now, I promise that, I will show you the always block, but also for what? For the test bench. What will be actually the use case for the always block and the test bench? It will be for generating a clock. So we know that the clock is a train of pulses, right? How I'm gonna do this in the test bench, right? So normally I will have initial begin, this block, initial blocks like this. And that will be taking care of the reset and I, the value of those. But we need another thing, which is gonna be generating a clock. We need the clock to be generated, right? So always begin. Normally what I do, I go in here and I say what? Initial begin. And I say what? Clock TB was equal 0. Then I go inside this and say what? Every 5 nanosecond clock TB is equal to the clock TB. What is that? What's the problem?
Equal to not clock.
Yeah. Sorry. Yes. So what does it mean? Those two together created the clock. How? The clock end of the day need to have a value in the beginning, right? Something to start with. I would say make it 1, so it will look very fancy, So anyway. Then I'm saying go in this always block, and every 5 nanosecond flip the value. So if it's 1, after 5 nanosecond, flip it to be what? 0. After 5 nanosecond, flip it again to 1. So it will end up being what? 5 nanosecond on, 5 nanosecond off. So that means the t will be equal what? 5 plus 5 is 10. If you flip it, you will get your maximum frequency. Are you guys following what I'm saying? Hello? Do you understand what I'm saying or not?
Yeah.
So what I'm saying is the following. I made initial for the clock TB equal 1. Then I said from now on, every 5 nanosecond flip. But I said the clock, it has a period of on and off, but they're equal because 5, 5. So end of the day, that the t, which is basically the periodic of the clock, is what? 5 plus 5, 10 nanosecond. So that means 1 over 10 nanosecond, it will be what? 100 maybe megahertz, something like that. So this is actually the 100 megahertz. Okay, now we made the clock. We need to the reset, right? So the reset is gonna be what? So we'll say reset TB equal 1, because I like to reset while my I, better for me to start it with something which is 0. Then maybe after 100 nanosecond, reset TB equal 0, and maybe after 10 nanosecond make there is no, of course, I, it has to be TB. Then maybe you can make I TB equal 1, right? Then after 100 nanosecond reset again, TB equal 1. After 100 nanosecond, finish. Okay, let's test what I'm doing here. There's an error here. What is the error? No, the error disappeared. So now we're gonna go and say what? Run simulation, behavior simulation, and see what will happen. Take some time, sorry about that. Okay, it opens. Let's see how it looks like. Here we go. It didn't come out. You know why? Because last time, if you guys remember, I saved the values of the signals of the old system. So basically I have to go back here, like, and just do like that. And then I say save. And then I reset like this. And I say run. Something is wrong, which I wanted to be wrong. And let's see why there's something wrong. How can I make this bigger for you guys? 1 second. Okay. So look, it gives the I is Z, right? The I is Z. The value of the ITB is correct, but then the P affected by I. Who made this I? That means, you know, there's something not correct connected, right? Which is correct here. This should be TB. See? So, you know, the test bench caught the error, right? So if I go ahead and run like this, that show you, even, you know, in a test bench, you can pass the test, even that I wrote I. Even there is nothing, it's called I inside the test bench, but it passed it. Let's see what's happening. Look. Much better, right? Any question? Any question? No. Have you seen this? This is actually cool. I'm looking for somebody to ask about this.
Professor, I have a question about the test bench.
Yes, sir.
How come, can you go back to the code? To the test bench code?
Yeah, let me just get to the test bench. Yes, okay, go ahead.
How come for in line 35, we used equal and not less than equal?
It doesn't matter. This test bench, the rules that I give it to you, it's not equal or not equal in this bench. This bench is just this bench. You can write C code as a test bench.
So in line 53, we can also use just equal.
Here. All right. Then let's run it again.
So that less than equal to is only
Less than equal is actually what's called non-blocking, right?
right. So that's only for RTL.
For sequential.
Got it.
Have you noticed something also? Do you remember that little red thing? It was there.
Yeah.
It disappeared, right? Why? As I told you, you know, this the regulation in RTL is not belong to the test bench. I can write a C code actually for the test bench. I don't need even Verilog. And then, you know, I can wrap it up and just test it, you know. Which code you want to see, Nathan? The test bench? Here, go ahead. Any questions, any problem? Let me know, let me know.
Professor, so was the red thing that disappeared? That's not an error, right?
No, it's not error. It means don't care. It shouldn't be even a problem. It's a problem about the prioritized reset. That's something we're gonna talk about later, but I don't want to pump too much. Luke, yeah, you told about the CLA. I leave it for now. Leave for now until you guys get the best knowledge of this, then you know I can go for the CLA because you have to know the flip-flop first. Okay. Any question? Any problem? So how are we gonna make this circuit? Sorry, how can we gonna make this circuit what generic or parameterized? Any idea? How can we do that? So I believe if you go ahead and say add source, create, and then you just say, you know, in bit register, right? And you finish, they're gonna be what? Still a clock, still a reset, is still input, which is port A, but this one is gonna be a bus because you know it's multiple registers, right? Let's just put a value now and I'll fix it later. And then you know here you're gonna be port C and it's gonna be the output. Let's make the same thing. Okay, let's see what will happen now. So we're gonna use the for generate this time with the module of the 1-bit flip-flop, and we can see how it's gonna look like. That makes sense? So in that case, I'm gonna take again a copy of the D flip-flop module here, right? Copy. And I go in this one, the end. DD flop, DDFF gen. And then you know we're gonna remove those. Right now, is this register synchronized or asynchronized? What does it mean synchronized? That means every single element or storage inside the register is using the same clock. So imagine that if I have many flip-flops and all of this connected to, you know, in and out, that's called parallel in, parallel out, right? That's a register, right? That's one of the configuration that we learned in 2300. So, you know, in that case, I can just say clock as it is. And it should have the same reset also. Our problem is actually the I and what? And P. And in this case, it's gonna be what? Port A, port C. But now we're gonna be allocation. And we're gonna go here and what? If you guys remember, gen var I for I equal 0, comma, I less than data underscore size, comma, I equal I plus 1. Begin. And generate, and there is generate. Right now, What is this data size? It's gonna be the parameter we're gonna make, right? -1. -1. Right? Are you guys following me?
Yeah.
I did exactly the same thing we did last time in the full adder, right? And now we're gonna be just I. Let's see what will come out. If you open here,
Oh,
Give
you
us-
didn't add the parameter at the top.
huh?
Line 23.
Something is not correct. No, it's correct. I'm looking to the wrong circuit anyway. So I have to say this at top. And look here. Now we have 16 what registers. If I go here and just say 128, right? Any questions so far? Hmm? Is there any question? How can you make a test bench for this? That's gonna be the last part of today lecture actually, because after that we'll be done for today. So we're gonna go in, add source, create. I'm just call it what, n bit register test bench. Yes, okay, finished. Good. We take a copy of this. Copy. And we'll go like that. Then let's go into the simulation. And we select the guy to be the official test bench. We're gonna remove this. And we put a name here and we call it what? Rec test. Then we'll remove this whole thing. Right. Then you know that's gonna be dot. What we can do, we can just go also here and make what data size TB equal 16. Then we can take this copy. Put it there. Then I can just go like that. Why is it an error?
28 need to be the pound sign.
Which one? No, one second.
Yeah, on 28, the naming was correct. You just add the pounder.
I have this, yes, I have to have this, yes.
And the name back to there.
Yeah. Okay, that's it. Then we need to what? Again, the input will be just clock. Just a reset. Let's call them TB. TB. And then register data size TB -1 to 0. Port A TB. Register. No, not register. Why not? Data size TB -1 to 0. Port SC. Then we're gonna take these names and put it there, right? We'll fix this error later. Okay, no. Is there any error? No. Okay. Now we're gonna make the always block again, but for the clock, right? So initial begin clock TB equal 1. Then always begin and maybe 2 nanosecond clock TB equal the revert of the clock TB. That means the whole clock is 4 nanosecond. So 1 over it gonna be 250 megahertz basically. Then if you go there, you just go ahead and see what initial and right, and then there maybe we can make what port ATB equal. We need to practice the numbering, right? So this is how many bits is it? 16, right? So maybe we can just write 16s hexadecimal because you have 16-bit in hexadecimal. So how many it will be? 4, right? 1, 2, 3, 4. That's it, right? Reset TB equal 1B1. Then maybe after 100 nanosecond, maybe we can make integer I. Integer I, right? Then we can just go and say for I equals 0 to the I greater than 2 power of the data size, right? TB, comma, I equal I plus 1. You guys know what I'm doing or not? I have done it before in front of you in the full adder. Port A TB equal port A TB equal what? Equal I. Then give it like 8 nanoseconds. That means 2 clock cycles, and then make port C TB equal port A TB. Then give yourself another 2 cycles. Then by the end of the day, what's the formula? No, I'm wrong. I'm sorry. Yes. It's my mistake, yeah. Okay, anyway, done. Okay. Then maybe after 100 nanosecond, finish. What's the error now? No errors. Why there is an error? Happy now? Yes, happy. You define the time first, and then you put the value. Then it will flip back again, define the time, because the for loop go up like cyclic, right? Anyway, you know what I'm doing. Let me tell you what I have done here, right? I generate the clock, right? The clock is what? 250 megahertz. Why? Because the duration is 2 for high, 2 for low. That means in total 4 nanoseconds, right? Then I instantiated the thing, and then I make it generic based on that is bench data size also. And then after that I initialize the port A with zeros, and I just use this hexadecimal thing, so as a practice for you to know the number distributions. Then I make the reset is equal what? 1, right? With this circuit, it's better for us to go here and just also say reset TB equal 0, or like 1D0. Why? Because end of the day, you need the reset to go down, so any input will be equal to the output, basically. And then I would like to have many inputs. How can I make this? So the size of the whole entire register is what? Whatever, right? Data size TB, right? Then 2 power of it will give you all of the possible number of this register will be carrying. That makes sense?
The line 58, the exponent to that one, the possible combination.
What does it mean, right? What does it mean? Let's say my register is 8-bit. No, let's make it 4-bit, right? So this would, I need the value of the register to be 0 and 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 and 10 and 11 and 12 and 13 and 14 and 15, right? How I'm gonna do that? So I will say count from 0 to 2 power of 4, right?
Okay.
So now, if I would like to fill a register 8-bit with all possible values, what I gonna do? I will say from 0 to 2 power 8. If I would like to cover all the values of the register 16-bit, I would say from 0 to 2 power 16, and so on.
So this one is 2 to the 16.
I mean, I make it generic, right? So every time I would like to, if I change this value, I am not gonna change anything in this code anymore.
Yeah, yes, okay.
That makes sense?
Yeah.
Okay, let's run it and see if it works or not. We're in this one, right? So run simulation. it didn't present, right? Because I saved before, so I need to take a copy again. So you see, I'm standing in the test bench. If I stand inside the register, it will give me the value of the register. Can you see that? Look. So if you remember, inside the register, it was called clock reset port A, port C, right? And this is the data size, basically we decided. But if you go up here, see, it will give you the clock TB, RCTB, port ATB, and so on. So, right, I will just take those and I highlight it with shift and I click to the rest. And then, I will take even this is okay. Then I go ahead and drag it like that, save. And then I just go and say, start from the beginning. And then, maybe you can just go into what? Run. Okay. Let's see what happened here. What do you think? Cool, right? Now we are zooming, right? But we need to understand the values in a way that we can understand them, right? So we can just go ahead and just do like this. Radix unsigned. Port A, port B, port A, port B, port A, port B. We don't even need I. I is not important for us. Port A, port B, right? And now here's the values. Look, it was zeros. Then 11, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. See? So, I covered all of the values coming out of it. Does it make any sense? And of course, the reset just work in what? In this particular area. Look, up to here, up to here. So I'm resetting up to here. And after that, the values start moving, right? Because 0, it turned to be 1, that is became 1. Moving it 2, this became 2. Any question? Hello. You guys have any question? Okay. Everything looks okay. Everything looks clear. Now, how we gonna go in a board? That's a very good question, right? So I don't have the board with me. I've forgotten in my office, but I will show you how to do it, and then you can do it. We're gonna close this, and we're gonna look into this card. Yes. Which file we're gonna communicate with? Which file we're gonna connect it to the board? That's the question. So let this is close first.
The XDO or XDC.
Yeah, XCC, but which top module we're gonna be used? Is it gonna be the in-bit or whatever? So that's why that was my question. So are we gonna implement this on the board or just implement one of those? So let's say we're gonna implement this on the board, this one, right? This one, it shouldn't be 128 in this case. Let's make it something reasonable, because end of the day, if you're gonna work on the board, you already have a limited LEDs and multiple switches, right? So I say that just make it 16. So we can just have 16 switches and 16 what? LEDs, right? That makes sense? And then the reset will be what? A button. What about the clock? The clock, it's a little bit tricky. So look, now we're gonna open the XDC. Here is our file. It's just have clock, reset, and port A and port C, right? I'm gonna go in my XDC like this. And I say, where is the clock? These 2 lines. I will what? Clear. Then this name, it has to be same name as the file. So it's just clock like this. So far so good? Then we said, we're gonna use we're gonna use port A as a switches, port C as a LED. So gonna be here like this. Now 0, 1, 2, 3, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then the LEDs will be what? Port, no, that's it, this bench. They're gonna be the port C. Copy. And we'll just go in this and see what. And then you know the rest. Right? Is there anything missing? Reset. Take the reset. And then we'll look what else we can actually use to control button. Yes, we can take this one. Then that can be ready for what implementation. If you run the synthesis now, let's see how much it will take. Okay. The computer takes some time. I don't know. What about you guys? Your computer takes up much time also, or what? Yeah,
Sometimes.
take time, right? Yeah, just a second, Nathan, until this run, and I will go back to it. Maybe we can look into the XDC since it's taking forever. Anyway, let's go back here. So, which part you want, Nathan? Switches? Here. Right? Your input has to be switches. So you already have, you're gonna make input 16 switches, right? And this port A, so that's why port 0, port 1 up to 15. LEDs port C up to port 15. There is no even errors or critical errors. Oh, that's good. Yeah.
Professor?
Hmm.
For the names in the XDC file, are we getting them off the n-bit register file or the D flip-flop file?
No, this is actually the n bit, right? Because look, clock reset, and then port A, port C, right?
Right.
It finished. It takes 16 flip flop. Yeah, it makes sense because I use 16 actually what registers, right? Yeah, 16 bit, 16 flip flop. Yeah, that's correct. And we concatenate them and just like make them parallel input, parallel output, right? If I just go ahead and tell him run implementation, he will run implementation. Pretty much there is no way for the tool to optimize this more than that. So it will come out as 0 lookup table and 16 flip-flop. There is nothing combinational here. I can make it combinational if I add enable. If you add enable, that can actually add extra lookup table. You know what I mean? Where did you add the clock again? I didn't add anything. The clock is there. Here, look. It's already there. I just uncommented. And then, I remove the name to be matching the name of what? My file. Here it's called CLK like this. So that's why I put it here. See, look, CLK here and CLK here. Those two lines will instantiate the crystal on the chip to be working. Okay. Let's see if there is any critical K. No, nothing. Yeah, that's understandable. Yeah. Perfect. Should be done in a few seconds. If I have a board here, I don't know. I think I bought one here with the oh. No, it's in my office. Yeah, it's okay. I finished. See, 16. But unfortunately, I don't have a board now, so generate the stream is not really important. So anyway, you guys have any question so far? Is there anything that's not clear?
Just need to practice.
Exactly. This course is based on practicing. If you practice enough, you will be perfect enough. That's it. Okay, I think that would be enough for today. I don't want to push too much, especially you guys going from in person to online in person. So let's see what the situation will be. But yeah, I think that will be fair enough for today. So what we learned today, we learned the always block. We learned the beginning of the behavior modeling, and we study use case of it is sequentialism, and we look into the blocking, non-blocking, and we practice more the for generate and the for loop in the test bench level, and the for generate in the RTL level. So that's it for today. Thanks so much. Any question, any problem, let me know. Copy of this presentation, I will put it on this recorded video will be on YouTube, and I will put it on one of the modules of the class on campus. Okay. Sounds good. Thank you, guys.
Thank you, Professor.
Thank you. Bye-bye. Thank you, Robin.